second. Yeah, Pradeep, are you able to hear my voice?
Yes, sir.
And the screen is visible?
Yes, visible, sir.
Okay, then we'll wait for 5 minutes and then we'll
Yeah,
start.
sure.
Okay. Okay, we shall start. So, yeah, I am audible, right, Pradeep?
Yes, sir, you're audible.
Thank you. So yeah, so today we'll discuss something about boundary layer. So as the name suggests, this phenomena is associated with the boundary. I mean, in this context of this course, it is basically a solid boundary, and as like from the name you can just guess it, like boundary layer. So that means there is some layer which is close to the boundary. For example, if this is a solid plate, or you know, let's say flat plate, most of our discussion will revolve around flat plate or maybe circular pipe, something like that. But there are some cases, for example, spherical bodies or irregular shaped bodies, streamlined bodies like aerofoil of wing of aircraft, etc. So there also these governing equations are valid, but various assumptions that we take are not valid in all cases. So that also we have to discuss. We'll take some problems. Before that, just briefly, I'll try to talk about this boundary layer. So basically, what they do, like so far, the story that we have been studying is like we first had Bernoulli equation, uh, and then Euler equation. They were applicable for inviscid flow, so they neglect the effect of fluid viscosity over the flow passage. But in reality, there is a fluid viscosity associated with any real fluid. Then in that case, what they typically do is, if you look at it, you will see this diagram in number of places around the standard books, fluid mechanics. But basically, what I'm trying to convey is, like there is a reason behind, like there is a story. Basically, you start with inviscid flow because that is easy to solve. Viscosity effects are difficult to incorporate. So what they do, they assume that, let's say this is your free stream velocity, which is u infinity, and let's say this is your 0 comma 0. This is your y coordinate and this is your x coordinate. This is a typical setup. This is a flat plate, and what they assume is, in this region, which is highlighted like this, they assume it as a inviscid region. So inviscid means there is no. Pradeep, can you please mute yourself? There is some background noise. And what is basically done is, the effect of viscosity, which is predominant uh, in the region where it is close to the solid wall or solid boundary, there it is considered as important. So basically, uh, in this region close to the wall, okay, one second. In this region close to the wall, uh, viscosity, or maybe I should write fluid viscosity effects are analyzed. So this is the, uh, you can call it as viscous region. I'm not saying the boundary of the plate, like maybe I'm writing it here, so maybe I should write it above the solid structure. Somebody may get confused. Viscous region. So basically, what we are trying to do here is we are trying to connect two things, which is one is inviscid region, where we don't consider viscosity, and there is a boundary layer which is close to the boundary, which is a layer where you consider viscous effects because of the fluid viscosity as the dominant physical phenomenon. So that is a nutshell what is boundary layer. So since there is no viscosity in the inviscid region, we assume that it has a constant velocity as well as the pressure is you don't have any, you know, change in the velocity. So this infinite velocity, it doesn't change with respect to x or y or anything. In this case, it's basically an x-directional flow, so maybe it's not correct to write with respect to y because there is no y-directional flow here, basically. Yeah, so these are basic assumptions. And then the second case is a circular channel. That is also a typical case. So basically, if you consider a center line like this, and if you have a pipe of diameter or radius which is shown here, so this is the cross-sectional area. So this is the boundary now, and this is your r equal to plus r boundary, which is the radius, and this is your r equal to minus r boundary. And let's say fluid flow is happening like this with this u infinity. So typically, this is a case of circular pipe flow. Here, what happens? Like assuming boundary layer is developing initially. So in that case, what happens? It develops till some length and it merges with each other. So like this, it should be a symmetric profile because otherwise it's not, the velocity and shear stress conditions will not be satisfied. So basically, this is your boundary layer, and after this point, there is, we call this flow as fully developed flow because there is no change in the velocity of the fluid flow with respect to x direction, or in this case the axial direction. So yeah, I think I saw one question in the assignment which says what is the maximum length that can be maximum height that can boundary layer achieve in a circular pipe. So it is basically the radius of the pipe, because after that the boundary layers merge and they become like one single flow, retarded type of flow. That is one question. Yeah, and in this figure I forgot to mention, so this region where, maybe I should use some other thing. So yeah, so this region where you have, like there are three type of flow regimes basically observed in the classical fluid dynamics problem, and I'm sure you must have heard about them by now. So this is called as the laminar flow. Then there is a transition which is in between, and then there is a turbulent flow. I am not going into the details of these flows because we have already spent enough time previously on this. So we'll have the discussion precisely about the boundary layers and different techniques that are used to solve them. So this is like basic introduction to boundary layer if somebody has not yet understood it. Okay, so now to analyze boundary flow, boundary layer, there is a boundary layer theory, and the important assumption for boundary layer. Okay, 1 second. Yeah, maybe before introducing this short form, I'll just write full form once. Boundary layer, we'll call it as BL going forward. Importance of boundary layer theory is delta is very small than the characteristic length or radius. So basically this is characteristic length. So that depends on the problem at hand. If it's a pipe flow, it should be radius. If it's a flat plate flow, it should be length of the flat plate. And what do I mean by delta? Delta can be shown for just illustration purposes. Delta is this, the height of the boundary from the solid boundary. And here it will be somewhere like in this region. So this is a standard convention that we use delta for boundary layer thickness. So this is a very important thing that many people forget over the time, because you do multiple advanced level calculations, but you basically forget
one question, sir. So
yeah.
you mean to say that in fully developed flow there is no boundary layer?
No, boundary layers merge, and that is, see, boundary layer exists if there is a boundary. So basically, see, I've shown here, right? Maybe I'll use some highlighter or something. 1 second. Yeah, so boundary layer will have a meaning only till there is a boundary between the inviscid region and the viscous region. But in case of pi flow, what happens after certain length? There is no separate boundary as such, right? Here you see only a single type of flow. So in the fully developed flow, there is no like you cannot define boundary layer there because there is no separate inviscid and viscous region there. So it's like a single phase flow with some mean velocity and some. So basically, earlier we were doing some calculations, right, where you get a parabolic profile in this region like this. So then that becomes that similar problem that we solved earlier, where you get parabolic velocity and with some mean velocity with maximum is twice the average, like that. Okay. In the developing region, what happens? I mean, in general, boundary layer, or the fluid in the boundary layer is a retarded fluid because of the viscous effects. So in general, yeah, thank you for asking this question. I forgot to mention one point. Typically what happens in this region, 1 second, in this region you will have a flow of fluid, and in this region also you will have some fluid flowing. But what happens in the boundary layer, the fluid velocity gets reduced because of the viscous effects. But if you compare the mass flow rate at the entrance and let's say at some point, some section away from the entrance and before the fully developed region, mass flow rate should be same, right, because of the mass continuity. So what happens because of the retardiness of the fluid in the boundary layer, uh, the fluid in this region, maybe I'll show something like this. The fluid in this region gets accelerated. You understood my point, right? Because the boundary layer fluid, uh,
Yes.
it is being retarded because of the viscosity. So this is also one question that is asked. I have seen in some competitive exams. Before fully developing, uh, you can draw a profile like this. Maybe I'll try. Actually, I should have used more space, but anyway, I'll try. So, if you, maybe I should have. Yeah. So if you see here, or maybe I should not write it there. It will become too clumsy. Uh, what am I doing? Sorry. So yeah, basically that is the point that is important. So yeah, coming back to this thing, this is the very important assumption, basic assumption that our whole theory is based upon. So remember that. So the coming analysis is valid only if delta is very small or not negligible, but very small compared to the characteristic length. So there are three ways to analyze. I should say methods. Methods to analyze boundary layer. I don't know. I am always confused whether it is Z or S. Anyway, first is scaling analysis. Second is similarity solution. And third is integral based methods or method. So, I mean, these are like three techniques that we typically come across when we talk about boundary layer. Yeah, I mean, you must have seen in the class. So basically, uh, scaling analysis is nothing but 1 second. So this term, I mean, this analysis earlier it was not that much taught in the undergrad classes. Right now also it's over like basic or introduction only. But this is very important analysis, and it's not only constrained to the fluid mechanics, boundary layer physics. The scaling analysis is used in almost can be used in almost all of the uh, physical phenomena. So basically, uh, what you do is based on scales, important terms in the governing equations are further studied. So basically, what happens, what you do is you develop some scale. I'll show you in some time, and you realize that one term in the governing equation is not as important as the other term. So what you do, you neglect that term. You assume that it's not that important, and you study the remaining, which is the significant term. So basically, in boundary layer, let's say you want to apply mass continuity equation. So this is our typical mass continuity equation for incompressible 2D flow. So what it does is in scaling analysis, you assume scales. So basically you assume your horizontal velocity scales as your main domain velocity, free stream velocity they call it. Your vertical velocity scales as some maybe v infinity. X scales as what is your characteristic x length. It is the length, let's say for flat plate. We are studying first case as a flat plate. And then your y scales as the boundary layer. Correct, no? Because like maybe this you can refer back to this image. So what you do is basically for any physical parameter in the governing equation, you take it some scale. So basically for the x direction velocity, you take u infinity. For y direction, we define v infinity. And then for x length, which is along the plate, you define it as length of the plate. And y direction, which is the boundary thickness, that is the scale for it. And when you do that, you put them back here. So here what it is, it's u is u infinity. So first term. So they use this uh, significant symbol. So that is called as order. It's not zero, it's not capital O, it's just a symbol which represents order. So and x scales as L, this guy scales as v infinity by delta, and the last term is of the order of 1. So 0 is not 0. In this analysis, 0 is considered as order of 1 because uh, this is like order. If it is instead of 0, if there is 100, then we consider it as order 2, like that. So you need to consider that way. And basic laws of physics or the governing equations that we studied or dimensional analysis, whichever you want, these terms should be of same order of magnitude. So what you do is for same order of magnitude, and that will happen only when your u infinity by L, that ratio becomes more or less similar to v infinity by delta, right? Then only these two terms will be of same order, otherwise they won't be. And then if you solve, you get u infinity or maybe v infinity. You get a scale which is u infinity into delta by L. And the very important assumptions, one of very important assumption for the boundary layer is delta should be smaller as compared to L. So uh, we want delta should be smaller than L. That implies your delta by L should be less than 1. And if you use there, therefore your v infinity should be very small than the u infinity. So now you understand, right? therefore, I mean, strictly speaking, uh, it's a 1D flow, so we should not consider V infinity only. But even if we consider, let's say, some velocity V infinity in this domain, it is very small, so we can neglect that. So basically, this is what order of magnitude analysis is. Uh, I mean, I'll just give you one. Like there are many things that can be, studied using this. But I'll give you like simple uh, things. You might have seen them. So like I'll try to go fast, but if you have any doubt, you can ask me. Uh, so basically, what you then next do is you do this procedure for all the governing equations. Okay, not only for continuity. You can do it for, let's say, for x momentum equation. So what is the x momentum equation like in the Navier-Stokes is you have u del u by del x plus v del u by del y, that will be equal to 1 by rho del p by del x plus kinematic viscosity, which is mu by rho, into del square u by del x square plus del square u by del y square. This is the typical equation that is used, right? And maybe you can take minus sign also. Here you take typically minus sign because this del p by del x is a negative quantity, and to compensate for that, you take minus sign here. Now here also you apply that logic. So there is no fixed rule. Okay, in one place you can see some other way of doing it. I am doing it differently, but the whole idea is you draw your own conclusions based on your analysis. So here what will happen? This term will become uh, equivalent to, I will not use this term because otherwise it will become too clumsy. So this will be u infinity multiplied by u infinity by L. This term will become v infinity multiplied by u infinity by delta, which is your boundary layer thickness. Here, this 1 by rho remains as it is because it's a density, you cannot scale it like that. And let's say you have some delta p base and you have some length L. So that will be your measure of delta p by L. We'll take the negative sign also. Here, the first term becomes kinematic viscosity into u infinity by L square. And the second term becomes kinematic viscosity u infinity by y square, which is delta square. In second derivatives, you only take the square of the length scale. You don't take the that quantity which is being derivated twice, because the quantity is derivated twice, so it should be taken once, but it is derivated twice, right? So the denominator should be the square. Now you have these 5 quantities, so you can draw a lot of conclusions from here. First of all, look at these two terms. Yeah. So if you look at these two terms, what you can say? You know that, right? We have delta, which is very, very small than L. So therefore, delta square is also very, very small than L square. And 1 by delta square is very large than 1 by L square. This is just from our assumption of boundary layer. And therefore, u infinity by delta square will be large as compared to u infinity by L square. So therefore, out of these two terms, which are highlighted here, these two terms, the first term will be almost negligible, because the other term is very large as compared to the first term, so it can be neglected. So this is like one approximation that comes out of the scaling analysis. Then what else can we do? So this is basically nothing but u infinity square by L. So yeah. and you can multiply gamma also, it doesn't matter. It is a positive constant, so the inequality remains as it is. Yeah, so now I can draw one more conclusion by comparing these two terms. So, as I said, their orders should match, right? So that will only happen when u infinity square by L is of the same order as 1 by delta P by L. I'm neglecting that sign because, or maybe I can take it, it's okay. So if you do that, what you get, LL gets cancelled and your delta P essentially scales as minus rho u infinity square. So you must have seen in some books, they define non-dimensionalized pressure as delta P by rho infinity square. So that comes from here only. You need not to think of something else. So enough of that. I'll come to the main part, which is uh, this thing what you call, that is of our main concern, which is you get yeah. So the important thing is, let's say you compare first term, which has this order of magnitude, and the viscosity term, which is of this order of magnitude, right? The last term, because the yellow term we neglect. So now, if you do that, what do you get? Yeah. So if you do that, you get delta square by L is of the same magnitude as kinematic viscosity by u infinity. You divide both side by L, so you get delta square by L square is kinematic viscosity divided by u infinity L. And from our previous analysis, we know this is the Reynolds number for length. I mean, x equal to L. And therefore, you have delta by L, which is scaling to the negative power of Reynolds number. So, the assumption that we take initially, which is delta should be smaller than L, that also means that Reynolds number should be sufficiently high. So these boundary layer theory will not be valid for a flow where Reynolds number is very low, and that is case in Stokes flow or plug flow, that kind of things. But for typical flows that are commonly observed in our surroundings, you can assume boundary layer theory as valid approximation as long as delta is very very small than L. And therefore, like in general, for in general, at any x, you have this delta by x, which is proportional to the Reynolds number at that x raised to minus half. And I'm telling you, many competitive exams have this. We'll take some problems. I can frame one right here. So basically, typically what they ask is uh, for a flow over flat plate, uh, assume it as laminar, or they don't typically mention all the things, but if nothing is mentioned, you can assume as laminar. Yeah, and I forgot to mention, we are studying laminar boundary layer here, because otherwise, uh, you know, one second. Yeah, since this is a scaling analysis, yeah, but since uh, yeah, this scaling analysis for 2D incompressible laminar boundary layer. For turbulent, actually, you cannot do this way. You have to take average velocity and then the time variant component. So that is different. So this is a laminar analysis, laminar flow. Anyway, so for typical question they ask is for a flat plate for a flow over a flat plate at 2 centimeter from leading edge, boundary layer thickness is, let's say, 4 mm, or yeah, it's okay. Then what will be the boundary layer thickness at x equal to, let's say, 4 centimeter? So basically, at one point, you know the delta 1. What will be the delta 2 at some x2? So you have to use this scaling principle. So we have, let's say, at x1, which is 2 centimeter, you have delta 1, which is 4 mm. And at x2 equal to 4 centimeter, what is the delta 2? This is the question. And we know that delta by x is proportional to the Reynolds number at that x power minus half. So again, you can simplify like this. So this will be proportional to the 1 by, or maybe I can directly write it as, what is the Reynolds number? It is u infinity x by kinematic viscosity power minus 2. So now, therefore, you can take this x there, and delta will be, so it is u infinity by gamma minus 1 by 2 remains the same because there is no change in these two parameters here. But x minus 1 by 2 and x, so that becomes x power 1 by 2. So therefore, you have a relation which is delta 1 by delta 2 will be x1 power x1 by x2 square root, proportional to the square root of x. And then you can easily solve these type of questions. So your delta 1 is 4, delta 2 is unknown, x1 is 2 by 4. I am not keeping the units same because anyway they get cancelled. So this is essentially delta 2 will be 4. So this will be 1 by 2. So it will be 4 divided by 0.5 root. So you can do the maths. So this will be the value. Okay, so this type of questions are framed, and you can, if you know the scaling analysis, you can compare the scales of two and you can solve them. Yeah, then the important thing, which is, yeah, so now going to the next scale, let's compare. No, before that, yeah. So you have written in x direction equation, right? One can write the y direction equation for boundary layer. I mean y direction, not Navier-Stokes equation. So that is typically del u. Oh, sorry. This will be u del v by del x plus v del v by del y minus 1 by rho del p by del y plus gamma del square v by del x square plus del square v by del y square. And again, if you do the scaling and scale v as v infinity, or capital I should write, if you do the scaling and you scale v as v infinity and u as capital U infinity, you know that v infinity is a very small quantity as compared to u infinity, right? That we did initially only, the first scaling that we got. So this one, and therefore what happens, all these terms which have this del v term, these term, and all these terms, they become very negligible. So therefore, what typically is conclusion of y-direction Navier-Stokes equation scaling analysis is, one second. So they basically what is conclude is, what we observe is del p by del y is almost equal to 0 in the boundary layer. So that means pressure is not a function of y inside boundary layer. So if it is not function of y, then pressure is function of x, because it's only xy, right? It's a 2D flow. It is a function of x only. And therefore, see, if you observe the image, so inside a flat plate boundary layer, you are saying pressure is only function of x. So I can again write it like there. Maybe I can just draw a simple figure here. So if this is your boundary layer developing, and this is your, y, x, this is your leading edge 0 0, this is your free stream velocity u infinity. So if I consider, let's say, any point which is at x equal to x1 in this figure, what I'm trying to say here is, yeah, and if I take, let's say, a cross-sectional area or line here, what this conclusion from the y-directional, means is, at this point, let's say pressure is equal to P1, and at this point also there is some pressure equal to P2. But since pressure is not function of y, P1 and P2 will be equal, as both are at x equal to x1. Are you getting my point? At any x, if you take a vertical line,
Yes, sir.
yeah, and therefore we mean that pressure is only function of x in the boundary. This is a very important finding if you are not uh, understanding it. But that means inside the boundary layer, pressure is not changing in the y direction at all. And that is one of the reason why we assume the delta is very, very small than L. If your delta is compared to L, then this scaling analysis will not be valid, because del P by del Y will not be negligible. Okay. Okay, so therefore, pressure is only function of x. And what was the point that I tried to make? Yeah. So again, P1 and P2 are equal, right? But P2, pressure at P2, that point is in the inviscid region. So this is inviscid region, right? So uh, in the inviscid region, Bernoulli's equation is valid, right? That we studied earlier. So from there, what you get, basically you get some P infinity, u infinity square by 2. I think there should be rho here somewhere, equal to constant. Yeah, I'm neglecting the z, because assuming the constant horizontal streamline. So here, if you take the derivative, then your derivative become d with respect to x. This becomes u infinity du infinity by dx. Yeah, and since P2 is nothing but P infinity, so basically, from here you can write your del P by del x is nothing but dp by dx. It is only function of x, and it is nothing but dp infinity by dx. But because at any x, p and p infinity are same only. So therefore, because of this manipulation, your this x directional, this you had this 1 by rho del p by del x term right here. So that becomes dp infinity by dx, and you replace this term I'm talking about, and you replace this term with d u infinity du infinity by dx. So I'll write it. You'll see the advantage. X direction Navier-Stokes equation reduces to u del u by del x plus v del u by del y equal to minus 1 by, yeah, so this 1 by rho will get, it will be here, and yeah, this will be minus here. So basically this minus sign will go away now, and this becomes u infinity du infinity by dx plus gamma del square u by del y square. The other term also goes away. And in flat plate, uh, u infinity is typically constant. That makes du infinity by dx 0, and this term also goes away. So basically, you have del u by del x plus del v by del u by del y equal to gamma del square u by del y square in flat plate. I mean, not in flat plate, like wherever v infinity u infinity is constant, so it can be pipe flow, it can be anything. But typically, if it is a curved surface, u infinity changes because p infinity changes. There you cannot have this. I told you, right? Because of the centripetal forces and all, this p also is function of y there if it is a curved body, and there you will have this term. But here, in case of flat plate, there is no centripetal or centrifugal force or anything like that. So this is your simplified equation. So yeah, this is one thing that is important. Now, typically in some, uh, maybe I can just see if I have some problems on this, or should I take something extra here. Just give me a second. Because see, this is a, I mean, I can ask you numerical based on any part here, because as I told you, right, here only I made this question just from one scaling. I can make 5 such questions from another scaling. So like that, there are many questions. So let me just see if based on the part that we covered so far, can we have some questions. Otherwise, this becomes too derivative, and you might have, some of you might have seen this already. But just 1 second, hold with me. Yeah, to complete this discussion, so okay, you got a reduced form of your Navier-Stokes equation. That is well and good. But there is one important parameter also, which is called as wall shear stress, which is tau wall. And for Newtonian fluid, we have seen this earlier. This will be del u by del y at y equal to 0. 1 second, guys. 1 second. Yeah. So anyway, uh, so now you know, right? Again, you can use scaling here. So mu will be as it is. Now for u you have the u infinity, and for y you have the delta as a scale. And you know, 1 second. Yeah, typically based on this scale, what is done is, you know, you get, there is something called as a skin friction coefficient, which is defined as tau wall by uh, half rho u infinity square. So basically what you do, you put this scaling here, and you solve it, and what you get typically is 1 by under root u infinity x gamma. I mean, let's say in strict terms it should be L here. So basically the point I'm trying to make is I'm not going into the detailed derivation here because it will take a lot of time, and you can do this algebra because you have all the scales. So this CFX also scales as Reynolds number minus half, and you know, this is also important observation. Maybe this exact values, basically if you have seen, there are some von Karman or Blasius exact solutions. There you have CF equal to, let's say, some 4 point something into RE power minus 1 by 2. So this proportionality constant will change depending on the methodology that is used to solve the exact problem. That also we'll see sometime later. But the point I'm trying to make is, using the scales, you can solve many problems. You can get some idea about what to do. And that is the main thing about the scaling. So one thing is there. Let me see we can do any problems on this. Yeah, so this is a previous year GATE question. So the question is, it is a flat plate flow for a flat plate flow at x equal to, let's say x.
Sir, your screen not working, sir.
Okay. Anybody else having the same issue? Because I can see it is moving.
No, I can see. No, I don't. I think I can see it. I can hear also. It moving locally probably.
Is it moving, right? I just scrolled
Yeah,
up.
moving. Yeah.
Okay, so maybe I think there is some network issue. Wait for some time. If it is still persisting, you can tell me. Coming back to the question. So the question, it is thoda, matlab, it's a tricky question, not difficult. It's a tricky one. So at x1, oh, it's not x1. At some x, delta 1 is 1 mm and Reynolds number at this point is 1000. Then fluid flow velocity is increased by a factor of 4. So the flow velocity, which is u infinity, increases to the 4u infinity. Then delta 1, or not delta 1, I should say delta at same x will be. So basically in this case they have not changed the x. We are at the same x location. They are changing the fluid flow velocity u infinity. So this is also one question that can be framed like this. So we know that delta by x is Reynolds number power minus 1 by 2. So here and again, if you do this, it will be u infinity x by kinematic viscosity minus 1 by 2. So in this problem, x is not changing, kinematic viscosity is not changing, only delta and u infinity are changing, right? So you can take that scale only. So therefore delta 1 by delta 2 will scale as u infinity 1 by u infinity 2 power minus 1 by 2. Correct, no? just for the sake of solving, I'll just interchange 2 and 1. It doesn't matter. Okay, and then the problem is simple. So you know that delta 2 is to be found. Delta 1 was 1 mm, and this will not be a scale anymore. This will be the exact ratio. And the u infinity 2, it's 4 times, right? So this will be 4 power minus 1 by 2. And then what it is? What is the answer? Let me just confirm. Yeah, so this is nothing but 1 by 2, right? Because square root of 4 is 2 and that is 1 minus, so that will 2 come in the denominator. So basically your delta 2 is nothing but 0.5 mm. So when the flow velocity increases, your boundary layer thickness decreases. That is also an important observation from here. Earlier it was 1 mm, now it become half mm when the flow velocity is increased 4 times. That is the important observation. So like that, you can frame many questions. Yeah, I had saw one question. Let me remember it. That's important actually. Let me just recall it. One second, I'll just see if I can find it. It is basically related to this frictional drag only. Yeah. So the question is, yeah, again, the question is same. It's a flat plate flow. It has a length L. Okay, so for a flat plate flow, what is the ratio of the drag force on the front half of the plate to drag force on the rear half. So basically there is a flat plate of length L, and for first 0 to L by 2 there will be some drag force, right? And for last L by 2 to L there will be another drag force. That is what is asked in the question, the ratio of those two. So now this is another type of question. So in that case, basically it's I mean, you have to again think of it this way. So we know that we have this as I said, this CF is there, which is tau wall by half rho u infinity square, right? So that means your tau wall is nothing but half rho u infinity square into CF. And what is tau wall? Tau wall is nothing but the drag force upon the area. And for flat plate, what is the area? Area is nothing but the width into length, correct? No, we'll call this width as, let's say, B. So area is nothing but B. Oh, it again becomes BL, boundary layer. We'll use some another symbol for this. Let's say W. So this becomes WL. So now, so basically from here, what you can observe is, so the width will remain constant, right? It's not changing. So your drag force will be nothing but half rho infinity square CF into WL. Now in this question, U infinity is not changing, rho is not changing, W is also not changing. So the only variables that we have are CF and L. Now, earlier we studied, right? So basically you can, from here also you can write it like this. F drag in this case is proportional to the CF into L. Only these two parameters are there. And from earlier derivation, we know that CF is proportional to the minus half of Reynolds number. This part. CF is proportional to the minus half of Reynolds number. So if that proportionality is to be incorporated here, so this will become L will remain as it is, and this will become Reynolds number at that length or X, whichever point you want. Since we are talking here L, we will use L and minus half. So F drag is like this, and this is for total plate because we are using the complete length. So from here, what you can do, you can further simplify. Let's say in general, at any X, F drag at that X will be proportional to the X into Re power X minus 1 by 2. Correct? This is just a generalization of previous scaling or previous proportionality. Now you can use Reynolds number, which will be U infinity X by kinematic viscosity power half. So X into X minus half. So basically your drag force at any X will be proportional to the square root of X, because 1 in and minus 1 half, it will be like this, no? Yeah. So now for front half, X goes from 0 to L by 2, right? Half of the length. Then your F drag let's say I'll use first as the first half symbol. It will be proportional to the L by 2 power half. But now it becomes tricky how to calculate the last half or the second half. So typically you can't do that, that from X equal to L by 2 to L, I'll just use the formula. It doesn't work that way. For rare half, and that is the trick of this question, F drag will be equal to the F drag total length L minus F drag of front half. Okay, so what basically we are doing is we are calculating the total drag on length L and subtracting the drag that is observed for first half, and that will become your drag for the second half. So this will become your second half. Now this is nothing but your drag on the first half, which is proportional to the L by 2 power half. Correct, no? So now we can take the ratio because we have to eliminate the proportionality constant. Otherwise, we'll have to write the whole thing, and that will eventually get cancelled only. So in question, what they are asking us to ratio of front half to the rear half. So basically, we need drag force on the first half divided by drag force on the second half. So drag force on the first half will be some constant into L by 2 power half, and for the rear half there will be another same constant because other parameters are not changing. This will be total length because the drag on total length minus drag on half length. 1 second. Oh yeah. So it will be sorry, my mistake. Yeah, so it will be some constant which is again this half rho infinity square into W, that constant, into total length power 1 by 2 minus half, which was the drag on the first part, like that. So this proportionality constant gets cancelled. Sorry, because it's same, because other parameters are not changing. And if you simplify this, what do you get? Here it will be 1 by root 2 because this is square root of that, and in the denominator you have 1 minus 1 by root 2. So if you further simplify, this becomes 1 and this becomes root 2 minus 1. And we know that, root 2 is 1.4, and you can do the calculation, but this ratio is greater than 1 if you do the calculation, because it will be 1 by 0.4, that is greater than 1, right? So therefore drag on the first part is greater than the drag on the second part, and this is very important observation. I remember this question was asked in some another form in the GATE exam. So basically what this tells you is that if you consider any plate, the drag or the shear stress is not constant all along the plate. It changes because the length, the boundary layer thickness also changes with x power half, and that's why your drag force also is not constant throughout. And this problem proves that drag force on the first half is more than the drag force on the second half for a plate. And if you do the same calculation, you will observe the same thing for pipe also. So basically, the point is when the fluid is entering some boundary, boundary layer is just getting started, the shear stress at that point is maximum. And as the boundary layer develops, the shear stress goes down and down, and the downstream it becomes lesser and lesser. So that is one also important observation. So the point of taking this problem was not only doing the maths, the important key takeaway also you should remember. That is one thing. And yeah, coming back to the the pipe flow, it's a very interesting thing. What happens initially? There will be very high initially. So what I mean by initially, at these points, which are at just the entrance of the pipe, there the shear stress will be very high, but if you see, gradually it will decrease, and at this point and onwards it will become constant. So that is also one important question that is asked in many competitive exams. And in case of flat plate, it will be maximum here, and then it goes down, down, down. It doesn't become constant here, okay, in case of flat plate, but in case of pipe flow, it becomes constant after certain point where it becomes fully developed. And one important note that you should remember is this boundary layer analysis. I mean, this is a interview question in typical.
So what did you say? In the fully developed flow, from this, the shear force is not there.
No, it will be there, but it will become constant.
Constant, right?
Yeah. So one note is there. Typically, what we are doing here so far is we are assuming that at x equal to 0, u equal to 0, and that is okay. But what about the boundary layer thickness at x? So basically, the starting point of the plate or pipe that is x equal to 0 is a singularity. So I mean, this analysis basically what it means is delta is not exactly at 0 at this point. Okay, uh, delta approaches to 0. Maybe this is I mean, not that nuanced of a point, but what happens when the fluid, at just touches the flat plate, the shear stress or the velocity gradients are very high there, and therefore generally we assume that delta is also 0 there, but the correct term is delta approaches to 0 there. But for our practical cases, we take it as delta equal to 0 and we solve it. But in some interview, they ask it as, at what point the boundary layer theory is invalid. So the first answer is wherever the delta is equivalent to the characteristic length. And second, even if the delta is smaller than characteristic length, at the initiation point or at x equal to 0, typically it's a singularity point. The gradients are too high, and there we approach that delta equal to 0, approaches to 0, but strictly speaking, it's not 0. Anyway, so that is also one. In some competitive exams or interviews, I have seen that. Now, yeah, there is these important terms are there, such as uh, you know momentum. Or before that, I think there is displacement thickness, right? One second. Yeah, I think before that there is a displacement thickness. So basically, these terms, they are over the period of number of years they have been developed. It's not like they have come up over the period of 1 year or so. So they all have some significance. I may not be able to do the justice and cover all of this in this limited period of time, but let's focus to the context of this class. So there is something called as displacement thickness. And see, in many books there are different signs, but typically what I observed is, I mean, we can take this as the sign here. The formula is easy: 1 minus u by u infinity into dy, and you integrate it till the boundary layer thickness at a particular x with respect to y at a particular x. Then there is momentum thickness. You may already know these formulas, but there are some interesting insights in this that I'll try to just tell you. This will be capital U. So these formulas, I think,
the thickness will happen just above the this delta, sir.
one second, I'll get back to you. Not H. Let's say, I mean, this is not part of this course. Okay, let's leave it. Maybe it's not required here. There is something called as energy thickness also. So that is for kinetic energy. You define it that way. But let's leave it here because it will become too lengthy. So these are, first of all, these are all imaginary quantities. So these are not real. The only real thing is boundary layer thickness. This momentum thickness, displacement thickness, they are not real quantities. They are imaginary quantities, and they are imagined to study a certain characteristic of the boundary layer. For example, displacement thickness. So as I told you earlier, because of the viscosity, when the fluid flows inside the boundary layer, it gets retarded. It will not flow with the u infinity, which is the free stream velocity. So displacement thickness is nothing but it is an imaginary thickness measured from the solid boundary or the boundary at interface there into the boundary layer, and through which, if you assume that free stream velocity is flowing, the same amount of mass flow will flow through that thickness. there is another definition to it. They call it as, displacement thickness signifies the mass that is deficient in the boundary layer because of the boundary layer formation, basically. So there are many definitions, but many a times I've seen people forget that it's an imaginary thing. They think that it should be somewhere in the diagram, but it's not. It's just an imaginary construct. And similarly for momentum thickness, it is nothing but, what you call this momentum thickness theta. It signifies, uh, you know, by how much thickness, if you assume a fluid flow with u infinity velocity, free stream velocity, that will be having same momentum as the momentum lost in the boundary layer, like that. First is the measure of deficiency of mass flow rate in the boundary layer because of the slow velocities of the fluid, and second is the measure of loss of linear momentum inside the boundary layer thickness because of the retarded velocities or reduced velocities of the fluid flow in the boundary layer. So yeah, first point is imaginary quantities, and second is, for all these calculations you need some u by u infinity form, right? Otherwise you can't do anything. So what typically people do, they assume different type of velocity profiles, and then they solve these things. So to do that, I came across one question which was very generic. So what it said, I'll tell you. Yeah, so the question was, it was just like this: arrange the following in decreasing order. First was boundary layer thickness, then there was uh, displacement thickness, and then there is momentum thickness. Only this was asked in the question. They have not given any u by u infinity or any other thing. So the thing is, you know, uh, the point that I am trying to make here is, even though you need u by infinity or any velocity profile to calculate these quantities, but their magnitudes will always be in same order, whichever it is. That we'll find out while solving this question. But that is important observation. I hope you realize that. So typically, uh, you know, uh, like there are many velocity profiles that are assumed. Some assume linear profile, some assume quadratic profile, some assume cubic profile. So some assume sinusoidal. Anything can be done. But majority of the things that I've seen, uh, they observe for flat plate at least. They observe cubic profile. So they take u by u infinity as some constant a1 plus a2 into y by delta plus a3 into y by delta whole square plus some a4 into y by delta cube. So this is an assumption, okay? This is, as I said, there are many velocity profiles available in the literature. You can use any of them as long as you can solve them. Here you have four unknowns, so you need four equations, and you have at y equal to 0, that is your flat plate, your u equal to 0, that is first. Then at y equal to delta, which is your uh, boundary layer segregation front. Strictly speaking, it should be 0.99 times of delta. Yeah, okay. So this is also one question. So if you see any definition in the book, any standard book, they define boundary layer as, uh, you know, uh, when the boundary layer thickness becomes, uh, oh, sorry, this is wrong. uh, at y equal to delta, u should be equal to u infinity, but strictly speaking, it should be 99 time 0.99 times of u infinity. So this is the question, that in definition where it is written, they mention it as 99% of the free stream velocity, but when they solve the problem they take it as u infinity. Can anybody tell me why that happens? Why this discrepancy is there? Have you understood my question?
It is 99% wherever is there, like the below this, like the thickness will be where the point is there, like it's 99% of u.
Yeah, so I mean, see, the catch is let's say this is your flat plate and this is your free stream u infinity. Okay, what happens? So at this point it is u infinity. Maybe I'll take one second. Let me take this this point. So yeah, so at this point, and let's say at this point which is above the 2, what is the velocity? So we know that u1 is also u infinity and u2 is also u infinity, right? So then how do you say that boundary layer is ended? The point is, if I take u equal to u infinity as the end point of boundary layer, there are many points in the free streams where u equal to u infinity is there. So just to emphasize that we are approaching it from the bottom, it is defined as 99%, but we solve it assuming as 100%. The catch is because there are many points where u equal to u infinity is there in the free stream, like that. I hope you understood my point. So now coming back to this question, so these two boundary conditions we have, and also at y equal to delta, which is the boundary layer, you will not have any velocity variation, right? Because it will be constant. The velocity is constant, u infinity. And if you know, there are two ways to define the fourth boundary condition. If you see the boundary layer equation, x direction equation, which is given by this, let's say I number it as 1. So at y equal to 0, your u as well as v equal to 0, right? Because there is no velocity across the flow and parallel to the flow because of no slip boundary condition. Therefore, equation 1 gives del square u by del y square equal to 0. So these four conditions they use and they solve this velocity profile, and this is like famous, I think it's 3 by 2 y by delta minus 1 by 2 y by delta cube. Again, I am emphasizing that there are many velocity profiles, but this is like the commonly known velocity profile, cubic profile. I have not done the calculation. You can do that because it's a four unknown, four equation kind of system, and it should be straightforward. So what was my point earlier? Yeah, so yeah, this question, arrange the following in decreasing order. So here now you can do the calculation, right? Because you have u by u infinity here. So just to simplify the calculations, put y by delta as some some variable which will be, let's say, what should we take? Let's say we take it as neta. This is I mean, this will be used again also, but let's, for the time being. So that means your u by u infinity is nothing but 3 by 2 eta minus 1 by 2 cube. Now you calculate your displacement thickness, which was 0 to delta 1 minus u by u infinity into dy. Correct, no? Yeah. But now, since we have changed the variables, our boundary conditions and the integration limits will change. So at y equal to delta, your variable becomes 1 by the definition. And dy by neta is equal to d neta, because delta is only function of x, not y. So if you do that, what should you get? Yeah. So if you do that, therefore the limit will become now 0 to 1, because at y equal to delta neta is 1. This will be 1 minus 3 by 2 neta plus 1 by 2 cube of this. And into dy it will be delta into d neta. Delta is constant. So now we have to do the integration inside. So this will be eta minus, this will be eta square by 2. So this will be 3 eta square by 4. This will be neta power 4 by 8. And the integration will be from 0 to 1. So this will be 1 minus 3 by 4 plus 1 by 8. So this is 1 by 4 plus 1 by 8. So that is 3 by 8. Yeah. So this is 3 delta by 8. Now you do the calculation for this thing, momentum thickness. Again, the formula is like this. And if you change the integration limits as we did earlier, this will become 0 to 1. This will become neta. This will become, one second. Oh, sorry. This will become 3 by 2 neta minus 1 by 2 neta cube. 1 minus 3 by 2 neta plus neta cube by 2 into delta dn. Okay. So should I do the calculation, because it will take time? Anybody knows the answer? 1 second, I'll check. For cubic profile, right? Yeah. Oh, I have delta and CD. I don't have theta. Anyway, it looks like we have to do the calculation. So 1 second. Yeah. So anyway, we'll do this. Okay. 0 to 1. The first term will be as it is, 3 by 2 eta minus 1 by 2 eta cube. Then this will become 9 by 4 eta square. Oh, I missed one. 1 second. Okay. Minus 9 by 4 eta square plus 3 by 4 eta power 4. Then 3 by 4 eta power 4 minus power 4 by 4. Is anything getting cancelled? Oh, this should be square. Oh, no, sorry. This will be power 4 and this will be power 6. Yeah, 4, 2, 1, 3. Okay. So now, yeah, I think this should be fine.
We can do it, sir. No problem. We can do it.
Yeah, but I need the final answer.
Uh-huh.
One second, because the thing is, we have to show this now. What is the decreasing order? One to we got here. The other one is the important one. Let me just see. Momentum, thickness for cubic velocity profile. Maybe I should have chosen the simpler velocity profile. One second. Because in any competitive exam, if you have seen the question of this type, typically they assume linear velocity and solve the problem. Anyway, I think I found something. 1 second.
In the assignments, they have given the value of u by u mu actually. Yeah, u infinity. Yeah. The assignments.
So is that so? Anyway,
Yeah,
I think they are one step away on this. I will do this.
Yes, it's better. Yes. Yeah.
Leave it. So integration is 3 by 2. This will be eta square by 2 minus 1 by 2 power 4 minus 9 by 4 cube by 3. 3 by 4. Actually, this is same term only. 1 by 4, 7 by 7. So this integration will go away. This will be from 0 to 1. There will go delta. So basically, this is 3 by 4 minus 1 by 8, and this will be minus 3 by 4 plus 3 by 20 plus 3 by 4 minus 1 by 28. So this 3 by 4 goes. Then, yeah, 3 by 20. Okay. This will be 15. So this becomes 15 plus 3, 18 by 20, which is 9 by 10. And you have this in the minus. Okay. I'll use the calculator now. Enough is enough. So 0.9 minus 1 divided by 8 minus 1 divided by 28. So this comes out to be roughly 0.74 times the delta. And this guy was 3 by 8, right? 3 divided by 8, which is 0.375 delta. So therefore, correct decreasing order is, see, delta is the largest one, then you have theta, and then you have delta star. And this is valid for other profiles also. quickly if we can. Let's say if it is a linear profile, so this will be 1 by neta. So this will be 1 by neta square. So neta minus neta square by 2. So it will be half. So delta star will be half for linear, and for here it will be neta square. Neta minus neta square. So neta square by 2 cube by 3. 1 by 2 minus 1 by 3 will be 1 by 6. Okay. 1 by 2. 1 second, I'll do it for simpler. Maybe we are spending too much time here, but sorry. For you, if this is a linear profile, so it's just simple eta. In that case, what is your delta star? That becomes 0 to 1. Delta will be out. It will be 1 minus neta into d neta. So that is neta minus neta square by 2 to 1. So it will be half into delta. So 0.5 times delta. And if it is theta, then it will be 0 to 1. Neta 1 minus neta d neta. That is neta minus neta square. So this will be neta square by 2 minus neta cube by 3. Correct, no? 0 to 1. So half minus 1 by 3. So this is 1 by 6. 1 by 6 into delta. 1 divided by 6. So that is 0.167 delta. Okay, so here it is different. Okay, let me check the question only. From where I got that. 1 second. I don't want to make any incorrect statement. So that's why let me just confirm one. Whether this was this or one second. I'm not able to find the question. Yeah, so this is correct. This linear velocity is correct. It's 0.5 and 1 by 6. So here it is decreasing order is it should be delta. Delta is always bigger. Then delta star, then theta. So now I'm confused whether I did this calculation correct or wrong. 1 second. Let me just see. Yeah, in this question it was given that it's a linear velocity profile. It was not a general profile. 1 second. This calculation I'll check again, and if it is some wrong, I'll rectify it. Okay, but yeah, as I said, if this is correct, then we need this velocity profile to get the decreasing order. This velocity profile is very common actually. I should get its answer somewhere, but I am not. That's the problem to verify. Give me 1 second. If I find it, it's okay. Otherwise, we'll move on. We'll come back to it later. Momentum thickness. Actually, this question everywhere I have seen it's linear profile. They have not solved it for cubic profile. Easily, it's not available. I'm checking that only whether it's available or not. Yeah, it should be there. 1 second. Yeah. So now basically after this we have what do we have remaining? We have similarity solution and momentum integral, right? Integral based things. Just want to end this before going there. Cubic velocity profile. Momentum thickness, lambda. I think I did some miscalculation here in the cubic thing. This 3/8 is correct. The final answer.
The first one is correct, sir. This is correct, I think. This is correct.
So,
delta is equal to theta.
Yeah. For this, the correct answer I found out. 1 second. Yeah, so for this, if you do the calculations, I made some, I think, mistake here. The correct answer is 39/280 into delta. So if you do that, 39 divided by 280, that is 0.139 delta. So yeah, so typically, in general, this is the correct order. We have checked it for two, right? For cubic and linear profile. You can check for yourself for other profiles also, but typically this is the correct decreasing order that I wanted to show you. You can remember it this way. Like the more number of integrations you do, the lesser the value becomes. So in displacement you integrate once, right? But in case of this displacement momentum thickness, you have to multiply and then. So therefore that value reduces. Like that you can remember. Anyway, so moving on. See, similarity solution. How should I say? You will not get many objective problems from similarity solution because similarity variables. So basically what happens in case of boundary layer or any problem in which there is no like for example if it's a heat conduction in infinite plate, infinite 2D plate. So for such problems or even boundary layer, in boundary layer your y scale, which is boundary layer thickness, it keeps on changing, right? It's not fixed, whereas x is fixed between some length or something, but y length, y characteristic length, which is your boundary layer thickness, that keeps on changing for any given x. So in such problems where you have, let's say, infinite length scale or length scale which is changing in one direction whereas fixed in another, in those sorts of problem you'll see similarity solutions. So what they do, they define one similarity variable which is I mean, we have already defined it this way, but here it is not similarity solution like in earlier calculation. It's just a variable. But what they do typically, they define one similarity solution like this, and uh, they try to reduce the or get the bound on a scale that is varying continuously or which is infinite. So in this case, if you see, if I define neta as this, then what happens? Then they change every equation in terms of this parameter. I will just show you the form of equation. It's the calculations are not important for this course, but you should at least know what it is. 1 second. Yeah. So basically, this similarity solution, it was started by Blasius. He was a student of Prandtl. Uh, so when you study, in the class also, Blasius solution was given. So that person, what he did, he combined two variables which are y and delta. And as we know, this delta is a sorry, yeah. So this delta is a boundary layer thickness. It is a function of x only. So he combined two variables which are y and x and form a one variable which is this theta. And then what he did some experiments and he plotted this value. 1 second. So what he did some experiments for 2D laminar flow, and then he plotted one curve which was neta versus u by u infinity. So the two non-dimensionalized number he plotted, and what he observed was he was getting he was getting a fit. This type of variation he observed, and for different Reynolds number also he observed same uh, variation. So therefore he concluded that this u by u infinity is some function of neta or some function of y by delta. So from there the whole thing started, that everybody gave you velocity profile in terms of y by delta. Otherwise you can ask, right, why y by delta? I can define any other parameter, right? But this is what the basics which was given by Blasius. So this is the uh, plot by Blasius. So then what is typically done here is uh, they assume uh, this u by u infinity as some function of assume assume u by u infinity as some function of theta, and they assume it as a separable form, so y into g by x. So here it is basically y by delta x. So like that they assume it, and then what they do, they change all your governing equations in these two parameters and then finally solve that using numerical methods. For example, if you want, I can give you some uh, form. For example, let's say del u by del x, if you want to plot now, but now everything is changed, right? So you have to do it by separable variable methods. So this will become like this, okay? And now this del u by del n, del eta, it will be basically, this gives you u, which is u infinity into y by delta, right? And delta is function of x. So now, and this is nothing but u infinity into theta. So if you take derivative of u in infinity in terms of theta, what you get? Only u infinity, and d theta by del x will be y by del square minus over half, and then there will be del x by del x, because x is the function of delta is the function of x. Y remains constant there. Similarly, you change other parameters also, like del u by del y. So now del u by del y will become del u by del neta into del neta by del y. Now del u by del neta will be u infinity again, and your del neta by del y is del neta by del y. Neta is y by delta. So it will be only 1 by delta because y is the only parameter. And then you have, let's say del square u by del y square. That will be del y of del u by del y, right? One second, am I doing it correctly? Because this will become 0 otherwise. One second. This is what typically is done. They assume some similarity variable and they convert all your governing equation, which is given by equation 1, in the form of that equation, and then they solve it. So the derivation I have, but okay, I'll just give you the derivation, the exact derivation. But my point is, it is not relevant to the discussion of our course. But anyway, we'll do that. One second. U infinity into yeah. So instead of doing this way, they just assume some gx form is not assumed. So now this u becomes u infinity into some function of neta, right? So this del u by del x will become del u. This is del u by del neta, and this will become del neta by del x, which will be y into g prime. And del u by del y will become u infinity. Yeah, basically this is u infinity into f of neta into y into g dash of x. This is the form for it. And here it will be differentiation because it is del u by del neta, right? And in this case, this will change to u infinity into f dash of neta into g of x. And if you take the double derivative of this guy, you should get u infinity f double derivative of neta into g square. So you can cross verify this later, but this is typically the procedure that is followed here. And then they put in equation 1, we have this x momentum equation, right? U del u by del x, v del u by del y is nothing but equal to kinematic viscosity into del u by del y square, which we got from the scaling analysis. So if you put the terms here, and from here you can get the unknown here is the velocity v. So if you rearrange the terms, how do you get the velocity v? Del u by del square minus u del u by del x whole thing divided by del u by del y, right? So if you do that and if you simplify, you get some form for v, and then find del v by del y, and then it in continuity equation. So continuity equation is del u by del x plus del v by del y equal to 0, right? Del u by del x you already have from here, and del v by del y you get through this process. I'm not going into the exact thing because it will take a lot of time. It is available in any standard fluid mechanics book. So if you do that, what you get is g square, so function of this, then you get d by d theta into f double prime of theta, single derivative, first derivative, minus u infinity g prime of x by gx into f equal to 0. So this is the thing that you get, and what you do later is you do the separation of variables here, and if you do that, what you get is d by d theta into f double prime divided by f prime of theta. So this side becomes only function of f, and the other side becomes u infinity by gamma, which is kinematic viscosity, g prime x by ga cube of x. So this is the other side, and it is assumed as some constant because that is the standard process to solve these equations. And that constant, if you assume equal to minus 1 by 2, then you further solve them assuming the boundary conditions. And what are the boundary conditions? They are at x equal to 0. So at x equal to 0, your gx should approach to 0. Otherwise, your theta will go to infinity, right? Because it is y by delta. And other things are like that only. And your at y approaching to infinity, your this thing also goes to 0, right? One second. Yeah, so I mean at y tending to 0, this theta by y, theta is a thing but a function of y by delta, right? So theta will also go to the infinity. So here there is some confusion here. One second. I'll just check. Yeah, at x equal to 0, delta is 0. Yeah, so at x equal to 0, matlab, one second, like slightly positive value of 0, this g, your, at x equal to 0, your boundary layer approaches to 0, and therefore, see here, this y by delta, so when your delta goes to 0, your y by delta goes to infinity. Basically, your one second. Maybe I'll solve this equation, then only it will become clear, otherwise it's confusing. So you do one thing, you assume it as some constant k, and you solve this equation. So what you get is g power minus 3, g is also function of x, into dg of x by dx equal to some constant k gamma by u infinity, right? This is a constant. So now you integrate the terms with respect to x, therefore you get g minus 2 power x divided by minus 2 equal to k gamma x by u infinity plus some constant c, and at x approaching 0, your g should approach infinity. Then only your neta will be g should approach infinity. At 1 second. Yeah, because typically this at x equal to 0, your delta approaches to 0, but here g is 1 by delta, so it should approach infinity. And if you do that, you get c equal to 0, and then you get g square as minus u infinity upon 2k gamma x. But this is a positive quantity, and this will be positive only if k is negative. So therefore they assume that k as minus 1 by 2 because it simplifies, that 2 gets cancelled, and what you get is g of x as under root u infinity gamma x. So this is nothing but if you this is basically your 1 by delta x, right? Ux by gamma is your Reynolds number. So therefore your gx is nothing but, if I take x out, this becomes u infinity by u infinity into x into gamma, right? So therefore your gx is nothing but 1 by x into rex power 1 by 2. So now you get it, right? So this is some function of Reynolds number. And then the second part, this part, this is actually the difficult one. Here they do some sort of they assume, I mean, this is a standard derivation, okay? I'm not doing anything new, I'm just giving you the nuances of it, because otherwise you won't understand it in first time. So what they do is that they then define some function. This is a process to solve it numerically. So if you don't understand, it's fine, and if you do that and do some calculation, what you get is third order non-linear equation. So this is also famous Blasius equation. You don't understand, it's fine, but you should at least remember it's third order and non-linear. Third order non-linear. And then what they do is, they use boundary conditions, which are at theta equal to 0, your f equal to 0, which is wall. Then at theta equal to 0, your u is equal to 0. That gives you your f as 0, and that gives you f prime as 0. This is no slip boundary condition. And as theta tends to infinity, you get u tending to infinity. Then you get f tending to 1, which gives you f prime tending to 1, and that gives you f double prime tending to 0. So these equation is solved, and finally basically then you get this famous Blasius curve. So so this becomes your solution, which is here it is f equal to 1. So where your u equal to u infinity. So this is your. अरे मैं busy हूँ, बाद में आता हूँ. I am busy. So basically, when your u infinity, u equal to u infinity is there, that becomes neta is equal to 5, and then you get this famous Laplace equation, you know, which is as follows: at neta equal to 5, y tends to delta. Therefore, 5 is equal to, or maybe before that, what we know is neta is y into g of x. This is our first assumption, and we got g of x as u infinity by gamma x by solving the other part of this equation. And if you put neta equal to 5 at y tending to delta, which is f equal to 1, then what you get is 5 equal to delta into u infinity by gamma x, and if you do the manipulation, you get delta x by 5 into gamma u infinity into x. So this is your famous Laplace equation derivation. You must have seen this, right? Some textbooks give the constant as 4.9, but here, just for the sake of ease of calculation, it is written as 5. But both are correct. Some people take it as 4.91, but this is a numerical solution, so that is okay. So so this is your famous Laplace solution. They call it as exact solution because it's solving. It is obtained by solving that this numerical equation using numerical methods. Okay. Now, we are already above the time. Okay, so this momentum thing is remaining, that we'll take up later. Next class, maybe I'll spend some time. But again, that is also not that difficult. The thing is, you may not find, numerical problems based on these derivations, and that may be boring for some of you. But yeah, this is the origin of these equations, and based on these equations, again, I can make many formulas or many questions, and then we can have that also. But yeah, coming back to this, then they derived this tau wall also, right, from this. So I think this is same thing like that earlier only. So CF is Rex power minus 1 by 2. Then you write CF as tau by half rho u infinity square, and then you get same formula. So that exact formulas are given in the class also, right? 0.664, 1 point something for CF.
It is given, sir. Many problems are given. Yeah.
Yeah. So I'm not going there. I'm assuming that you know them.
So actually, they did not derive this. They only gave the formula actually. the one they just derived now.
Yeah. So see that the point is, I am also skipping many steps in this derivation because this is not the part of this course. But anyway, at least you should know what is this, and this should be some this should be, there should be some bound here, otherwise it's not a correct. So this is 1 where your u infinity is equal to u, and this is also 1 where your y becomes equal to delta. So basically everything started from this plot. He plotted and he got the same thing for all different Reynolds number in the laminar region, and then this everything started. This is a okay formula. So okay, this last thing which is remaining, that momentum thing, momentum integral equations and all, that we'll take up in the next class. But again, there are no straight numerical problems based on that, but yeah, it should help somewhere. So okay, we'll stop today. I've already taken more than 10 minutes. So 1 second before just we close. Give me 1 second. Yeah, I mean, as I said, from earlier calculations, we know that, right, CF at any x is proportional to the Reynolds number power minus 1 by 2. And in this case, like what Blasius did, he also followed the similar derivation, but he got the constant, which was 0.664 Rex power minus 1 by 2. So only this constant value changes. In case of Blasius, is it 0.664, but in case of this one Karman momentum integral solution, it is 0.646, and one Karman used a cubic profile like that. Anyway, so same analogy. It is CFX is tau wall by half rho infinity square, and then you put tau wall as 3 mu u infinity by 2 delta, assuming the cubic profile, etc. And then you get that answer. Okay, this is for, oh no, this is not assuming anything. I think he has solved it. So okay, we'll stop here. We'll meet next class, which will be our last class. Okay.
Okay, sir. Good night.
Okay, Pradeep, good night.